Welcome to a new AG session all about analytic geometry. Let us try to prove that the points presented here, A at 6, -13, B, -2 and 2, C, 13 and 10, and D, 21, -5 are vertices of a square. Before we start, we have separate videos previously that talks about proving that the points are vertices, or again, same 4 points. 4 points are vertices of a parallelogram and a rectangle. Now, a square is both a rectangle and a parallelogram at the same time. Okay, so you might want to review those videos as guide in order for us to show the proof for this video here. Take note that in the showing the vertices of a parallelogram, we use the measurement of lengths. We could also use the slopes, but we picked length of that so that we could use the slopes better in the second video, the rectangle. For this video here, for the proving the vertices of the square, we're going to show both methods because a square is a special form of a rectangle. Aside from it takes the property of a rectangle to have 4 90-degree angles or interior 90-degree angles, it also follows the concept of the sides or the length of the sides as presented in the use of parallelogram last time. So here, let's try to plot all these points first on this Cartesian plane where each grid now would be 2. Let's try to make 2. Because we have here 21. That's a little bit longer because I only have 10 steps here. So we're going to make each grid by 2. And that, of course, the x-axis is our horizontal and the vertical one is our y-axis. So A is at 6 and -13 again. 2, 4, 6. Let's make it by 2. So we have -2, -4, -6, -8, -10, -12, -14. Somewhere here is 13. So 6 and -13. This is our A, point A. Our B is at -2 and 2. So -2 and 2. Sorry, 2. This is our point B. Okay. Next, again, let's check 2, 4, 6. 2, 4, 6, 8, 10, 12. Okay, that's right. And next is our C, 13 and 10. So 2, 4, 6, 8, 10, 12, 14. So 13 is here. And 10. 2, 4, 6, 8, 10. So the intersection is somewhere here. This is our point C. And I hope that I could come up with a nice representation here as I have 21. So you have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So I'm just gonna make it a little bit longer here. It's 20, 21. Let me check. 6, 13. Again, let me have 21. Sorry, 21 and -5 rather. So 2, 4. So -5 somewhere here. This is our 21. So 2, 4, -5 is here. Alright. Assuming that my illustration is correct and connecting all of these points. So A, B. Okay. We have B, C. We have here C, D. This is actually our point D, by the way. I forgot to label this. And then D, A. We have it here. Alright. In this illustration, we have shown that it's a quadrilateral since it has 4 vertices. But we are going to show that these 4 vertices are not just vertices of any quadrilateral, but more specifically of a square. So in order for us to show that, let's start by going to the concept of angles. Okay? It's because if this is a square, then this means that the angles, interior angles formed here should be 90 degrees. That's what we're going to show first. Okay? This means that the sides are perpendicular to one another. Okay? If we talk about perpendicular to one another, that would mean that we have to show here that the slope, the relationship of one slope to the other, its adjacent side, is that it's a negative reciprocal of the other. Okay? That's for the 90 degrees here. Now, if we're going to finish proof showing that these four are 90 degrees, we cannot yet determine that this is a square, because a square is a special form of rectangle where all sides have the same measurement. Hence, we're going to use the idea of the distance formula. So we have here this notation: the distance of the points, or the length of the segment, okay, is equal to, we have this formula, whatever second point you use, you will have x sub 2 minus x sub 1, you square that, plus you have your y sub 2 minus y sub 1, and you square that. And we're going to solve for the measurement of all sides, and for them to be a square, or for this to be a square, the lengths should have the same, all of the sides will have the same measurement. Let's start with the slope. Let's have the slope of AB first, okay, AB, and then the slope of BC, and then you will have here, hopefully my spaces are enough. If it's not enough, pardon if I'm going to make shortcuts on the computation. Again, it's DA or AD, it's up to you, but since we can call it, the name of this is ABCD, so that's DA. But of course, again, they're just the same. So the slope is, or has the formula, or the formula for the slope, I forgot to write the formula for the slope. It's y sub 2 minus y sub 1 over x sub 2 minus x sub 1, depending on which point you're referring to, point 2 and point 1. So for AB, let's pick B as our second point. So y sub 2 is 2 minus y sub 1, which is negative 13. Please not forget the parentheses. Over your x sub 2 for B is negative 2 minus your x sub 1, which is 6. So you'll have here your slope, that's 2, double negative property, plus 13, so you have 15 over negative 8. Or in short, you'll have here negative 15 eighths. That's the slope for AB. Okay. Next is the slope of BC. So we're going to pick C as our second point. So your y sub 2 is 10 minus your y sub 1, your B is 2, over your x sub 2 is a 13 minus your x sub 1, which is negative 2. Again, don't forget to place parentheses. So that's 10 minus 2, that's 8, over, that's double negative property, so 15. That's positive 8 15ths. So you might have another already idea here. But let's try to continue with CD. Let's have D as our second point. So y sub 2 is negative 5 minus, we have here 10. That's your y sub 1. Then your x sub 2, which is 21, minus your y sub 1, which is x sub 1 rather, which is 13. This negative 15 over 8 as well. And for our DA, let's have A as our second point. Now, if you're going to pick D as your second point, you will still have the same result. So let's have y sub 2, our A is negative 13. Our D is minus negative 5. Okay, don't forget the parentheses. Over our x sub 2, which is 6, minus, we have x sub 1, which is D. So we have minus 21 here. Okay. This would mean double negative property. You have plus 5, so you have negative 8 over, that's negative 15. So you have here the result of positive 8 over 15. Now we have all of these four slopes. Look at the relationship of specifically AB and BC. I'm talking about this angle here. Okay? AB and BC. Our AB is negative 15 eighths and BC is 8 over 15. Obviously, this is the reciprocal of the other together with a negative. In short, negative reciprocal. If we're going to multiply this with a negative, so it becomes positive, and reciprocate that, you will get this, and vice versa. If we're going to reciprocate that, that's 15 eighths, and add negative, you will have this result. This means that this line segment is really perpendicular to this, and that perpendicularity means this is really a 90-degree angle. Let's pick this second here. So we have CD and DA. So you have CD and DA has the same idea. negative reciprocal, so this is already proven. And finally, we have also BC and CD. We also have the same thing, even this and that. This means that all four angles here, together with the idea of the quadrilateral angle sum theorem, they're all to be 90-degree angles. Hence, they are perpendicular to one another. But it's not, again, enough to say perpendicularity because it's a square, not a rectangle. If it's a rectangle, we stop here, but it's a square. That would mean we also need to look at the measurements or the lengths of the sides, and they must have the same results. So let's use this space here to come up with the distance we have here for AB. Okay, let's use this formula here, the square root. Our x sub 2, let's have B as our second point. X sub 2 is 2 minus our, x sub 2 is negative 2 minus our x sub 1, which is 6. You square that, plus you will have here for your y sub 2, 2 minus, that's minus negative 13, and you square that as well. Okay, so you will have here, that's negative 8, you square negative 8, that's 64. Okay, then you have plus 15, that's 15 squared. Okay, that's double negative property plus. What happens then is you will have square root of 64 plus 225, 225, which is equal to the square root of 289. And we have a specific value for that. Square root of 289 is equal to an integer of 17 units. Okay, that's for AB alone. Okay, hopefully the space here would be enough. This would mean that this would also be 17, 17, and 17 here. If we're going to solve for BC, right, let's have C as our second point. Okay, C as our second point. You will have 13, our x sub 2 minus x sub 1, which is negative 2, and you square that, plus your y sub 2, which is 10, and minus 2. You square that. You will have here the square root of, that's 15 squared, okay, plus 8 squared. I'm not going to finish this because we have the same value here, okay, and therefore this is also be equal to 17 units. Of course, I could finish that, but since my spaces are not enough, I still have to show other two. You can continue that on your own, but basically you will still have 225 plus 64. You will have the next one, CD, is equal to the square root of, let's have it here for a lot, the last space for our DA. So D is our second point. You will have 21, that's your x sub 2, minus your x sub 1, which is a 13. Okay. You square that, plus your y sub 2, which is negative 5, minus your y for your D, your C rather. This is square root of, that's 8 squared, plus that's negative 15 squared, which is still the same value here. And finally, for your DA or AD, okay, square root of, okay, let's have A as our second point. So x sub 2 is 6 minus D, which is 21. You square that, plus your y sub 2, which is negative 13, minus your y sub 1, which is negative, y sub 2 minus y sub 1 minus negative 5. Yeah, that's correct. You square that. Of course, you will get here 6 minus 21 is negative 15 squared. You have here plus, by double negative property, that's plus 5. So negative 13 plus 5 is negative 8 squared, which was, again, will have the same result as this. So if we're going to continue all of this, AB has 17 units, BC is 17 units, CD and DA are also 17 units. So this shows that the sides have the same measurement together with earlier that are proving that the interior angles together with the sides are 90 degrees. This shows that our figure here is really a square, and this further shows that points A, B, C, and D are vertices of a square. Thank you for watching, and stay tuned for another session here in AG for Analytic Geometry.